Today we're going to talk about classification. So we're sort of moving on from our previous work in machine learning where we talked solely about regression to talk about classification now. Classification is dealing with machine learning tasks where there are discrete valued outputs instead of continuous valued outputs. So instead of predicting peak electricity demand, the continuous quantity, we want to predict, is this email spam or not, or which kind of picture, is it a cat or a dog we're looking at here. Now the good thing which we'll show, and actually sort of the main point of this lecture in some way, is the idea that if you set things up in the right way, this is not that different from what you've done so far with regression. And so in particular, we're going to set up classification such that it's essentially the same exact framework where we have a hypothesis function, a loss function, and a way of optimizing them. And the way of optimizing them will still be, for the most part, just gradient descent. So we'll go through all that. So we're first going to talk about an example of classifying tumors from statistics about the visual images of the tumors. Then we're going to talk about some classification in machine learning kind of generally. We'll talk about a few example classification algorithms. We'll talk particularly about support vector machines and logistic regression. And finally, we'll talk about libraries. This is for machine learning. I think that was an old title there. It should be libraries for classification. OK, so let's just jump in. A few announcements first. So there were a couple questions I've gotten about tutorial topics. And I decided to put up a link to at least the titles of the previous topics people used last time. So this is a link to the previous classes list of tutorials that they took. So you can go here, or that they submitted. The full ones aren't there. I just didn't want to put those too accessibly. Just the point is to work to basically have your own take on all of these things. But you can look at the subjects there and get a sense of what people worked on before. It's a pretty broad swath, and I actually sort of encourage some more than others. So I will, in some cases, when you submit one, I will give you a sentence, just like you give a sentence of what you're going to do. I'll give a sentence of feedback back, and you will have a chance to change if you decide you want to do something else. But of course, the more you change, the less time you'll have to do the tutorial. So be aware of that. The homework 2 solutions are released. Finally, we were a little bit late on this, but they're out now. They're on Piazza. Again, they're just images, so if you want to use them, that solution, you have to type up the solution. But in particular, there's a question on homework 3 that requires a solution for homework 2. So you can download the homework 2 solutions, type them up, and then use that as your solution for homework 3, or as part of your solution for homework 3. This last thing was a point of some confusion too. I think it was described incorrectly there. There was some confusion on our side on this, but you do not need to downgrade Pandas to run the homework. It is true that the AutoLab version uses an older version of Pandas, but except for some very rare occurrences of esoteric functions that you may use that were not in version 18 that are in version 20, which is what sort of is the current version in Anaconda, we don't see any problems there. So you don't need to downgrade your version of Pandas unless you really want to for some reason, but I wouldn't recommend it. You also need to use it. The older versions aren't in Anaconda, so you have to install like a virtual environment and downgrade your version of Python, all this kind of stuff. I just wouldn't recommend that. So don't. There's some mention of this, but there's no need to downgrade Pandas for homework 3. You can just use Pandas as it was and submit your solutions as they are. OK, any questions on any of these points? Logistics or anything like that? OK, let's jump in to classification then. OK, so when we talked last time about machine learning, kind of almost for visual reasons if nothing else, I gave the example of predicting real valued quantities. That is, our task was to predict something like electrical demand. And that's a real value quantity, right? It's going to be some real number, but in however many gigawatts we use electricity. And this is kind of nice because it's very easy to visualize, right? Sort of fitting a line to data, essentially, is what the regression task really is how we solved that regression task. In classification tasks, though, which are just as prevalent in machine learning to a large degree, now the goal is to predict some discrete valued quantity. So we have some quantity y. If we have binary classification, that quantity could be -1 or +1. We'll have an example of that in a second, but something like spam classification, right? It's either spam or not spam. It's not, there's no label you get saying something is 1.5 spam or negative 2.3 spam. You might come up with assignments like that, but you're not going to get labels of that kind, right? The actual labels you will get in your data set are going to be yes or no. There's also multi-class classification. Oh, and in particular, this is sort of actually an important thing to note, that I will be using -1 and +1 for binary classification, not 0 and 1. We may use a little bit of 0 and 1 later when we talk about probability, but for now we're talking only about -1 and 1. And the reason that is we're actually going to simplify some of the expressions for our loss functions based upon those values. So make sure you use those values and not 0 and 1. Of course, it's just notational, right? Of course, you can just do a translation to get between the two, but the formula I give will depend on them being -1 and +1. So be aware of that. Another setting is multi-class classification. This is where there are more than just two choices. So for example, if you want to predict what's objects in an image, right? You might be a cat, a dog, or a rabbit, or any other kind of animal, right? Any number of things could be in an image. And that would be a more natural setting for multi-class classification. Again, because there's no notion of sort of a scale of, this is halfway between a cat and a dog. There's no real notion of that. These are discrete quantities, just like we had, by the way, we talked about data visualization. This is sort of these are categorical variables. And of course, you can have more than one class you're predicting. We'll mention that very briefly. I have one slide on that because the reality is it's not the main point we're going to focus on. I want to focus on kind of the idea of classification more than the specifics. But of course, libraries like scikit-learn will handle the binary case as well as the multi-class case. So let's start off with a simple example here of a breast cancer classification task. So this is actually a really interesting, a very historically interesting classification task in machine learning. This came out in '92, and it was sort of actually one of the, it's a standard data set now, but at the time it was actually kind of a really interesting application of machine learning and a really compelling one. There's very little what we would sort of currently think of as advanced machine learning. We are going to be classifying cancerous cells from images. But the way this worked is that they had a manual program where the doctors would take a slice, they'd remove some fluid from a tumor, they put stain it and put it on look at it under a microscope. And then they would not do everything kind of a black box way, but they would actually look at the cells, and they would have a little computer program that let them kind of highlight those cells, say where the cells were, and then compute some very simple statistics from those cells. So in particular, they would compute things like the area of the different cells, the perimeter, the concavity, that is, are there areas where the cell kind of has a little indentation like that or not? And the texture, they had some features on sort of what the texture looked like. They computed all those per cell, and then the features describing the entire image would be things like the average of these different things, and the average area, the average perimeter, the average texture quantities, also the standard deviation and the max for all these features over all the cells that are in the image. Okay. And they did this, and they sort of had a manual computer vision pipeline to do all this. Now these days, you would probably think about doing this all with kind of end-to-end machine learning and computer vision in place using some sort of deep learning architecture. But back then we didn't really have that, or at least we couldn't really do that at the current scale. And so it's still pretty compelling that you could sort of even through a manual process extract some features like this from cancerous cells or non-cancerous cells. And the goal of this classification task is to predict whether these tumors are malignant or benign, whether they're growing and going to get worse, or whether they're benign, we don't worry about them. So again, I think this has been a really influential study, both in terms of now being a standard data set for machine learning, but also being kind of a really cool application even a long time ago about just how thinking about the impact that machine learning and data science could have in domains like healthcare. So what I'm going to show in this next slide is now a plot of some of these features, along with a labeling of whether the tumor is malignant or benign. So this is what the data looks like. Again, I'm not showing all of it because there are actually 30 features total here, and you can play around with the data set actually if you want. It will be in the notes when we put those up. But I'm showing right now two features. I'm showing the mean number of concave points. That's in, each cell may or may not have a concave point in it, and so this is the mean number of concave points over all the cells. Typically, there aren't very many of these, but when they are there, it's useful to know. And then also the mean area in pixels of the cells that have been selected. And so you can kind of see that you know, bigger cells are more likely to be malignant, and the more concavities there are, also the more likely it is to be malignant. That kind of makes sense because, you know, cells that are growing rapidly are malignant cells, and so they're also going to grow kind of in irregular shapes just because they're growing so fast, and so they're going to have these concave regions, and they're going to be bigger in general. And so this is one view of kind of the classification task of and I should say, you know, the blue X's here are the benign ones, and the red pluses are the malignant ones. And so our goal now is to differentiate between these two categories, between which ones are malignant, which ones are benign. And whereas your mental model for linear regression was all about kind of drawing a line through the data, your sort of cartoon picture for classification should really be about drawing a line that separates the two classes that we're talking about here. Okay? So what really is, and we'll define this a little more formally, I'll define this a little bit more when we talk about the actual sort of math behind these, how we do classification. But conceptually now, at least, when we say linear classification, what we mean is we're drawing a line not to sort of fit the data in the normal sense, because we're not predicting one of these from the other, but we're fitting a line to separate one class from the other class. And that should be your kind of mental model. And of course, it won't always be a line. When we have nonlinear models, it will be nonlinear regions we can sort of sweep out. But we're trying to separate the positive from the negative examples here. Okay? So this is one example of a separating boundary, and we'll talk about how we come up with these in a second. Any questions on that? Okay, so let's just jump right in and talk about classification in machine learning. All right, so the nice thing about classification is that as I sort of emphasized before, and this really is the main takeaway, hopefully it's the main takeaway from this lecture, is that when we go through the trouble of sort of setting up our machine learning framework, as we did last time, there's not a big difference between classification and regression. They end up being very, very similar, and you can treat them essentially in exactly the same way. So in particular, and I'll just write this again just to sort of emphasize this all, just as before, we have inputs. Let me just make sure I'm visible here. We have inputs, which are vectors in Rn. In this case, the input might be the mean, you know, at least in this figure here, in this figure, the input might be the mean area of the tumorous cells, the mean concave, number of concave points, and a 1. Remember, the 1 is how we capture the constant, the bias term, the intercept term. And we're going to have that, just like we did before in a linear model, we're going to have that here. So we have the inputs as before, where they're each an Rn, and there are m of these. So same notation as before. We have outputs, where here, the output is no longer a real valued number anymore. The output is actually in this case, binary number, -1 or +1. We have model parameters as before. And just like before, this is not true in general, of course, for all machine learning. But in this case, again, we're going to have a number of parameters that are equal to the number of data points. So they're both going to be n-dimensional. Sorry, not the number. Sorry, the dimension of the data points. They're both m-dimensional, n-dimensional. And this is going to be our vector that kind of defines our hypothesis, or the set of parameters that define our hypothesis function. And then finally, we have our hypothesis function. And this is actually really the only tricky part about classification is right here. So once you sort of understand why this is the way it is, then everything else follows pretty easily. So for hypothesis function, we'll say. Okay, and that is a function that we're going to write like this. It maps inputs to outputs, but it's actually not quite that. So it actually maps inputs to real valued numbers, not to 0, 1. So in the case of regression, our outputs were real valued, and our prediction was real valued. It kind of all made sense, right? And the error was just how far apart they were. And classification is a little bit different here. We're actually going to assume our hypothesis gives us outputs that are continuous, real valued quantities, where it really is the sign of the output that determines whether it's positive or negative. So if we predict a positive number in our hypothesis function, that means we're predicting a positive class. If we predict a negative number, that means we're predicting a negative class. Okay? The reason why we do this is that this lets us a few things. First of all, it gives us a sort of a natural way to measure how confident we are in our prediction. So if you predict a very large positive number, that kind of means you're very confident this example is positive. If you predict a very large negative number, it means you're very confident it's a negative class. And if you're sort of predicting 0, it means you don't really know what it is. So again, we're going to focus here on linear hypothesis functions. So we're going to focus on linear functions where this is equal to the sum from j equals 1 to n of theta j xj, which is also equal to, we also just write it like that. Remember, the inner product between x and theta. Okay, so that's actually the key point, is that even though we're predicting, even though our output is binary valued, we're still predicting a real valued quantity. And we do this basically because if you don't do this, it's very hard to take derivatives and things like this. Remember, we're going to solve this all with gradient descent. If you just predict a 0 or a -1 or a +1 quantity, then oftentimes small changes to your parameters won't change your prediction, and so you'll no longer have well-defined gradients to run gradient descent with. And there's also obviously kind of a nice benefit to having a measure of confidence as opposed to just a prediction. Okay, so now I want to map this formalism to this picture. Okay, and this is also important to understand. So what this picture is actually showing is this picture is showing in the red the regions where this. So these two axes here are both inputs. Those are the 2 dimensions of the input space in our case. There are really 3 dimensions, but one's just a constant term, so we don't need to plot that. These 2 axes on our plot here are showing the dimensions of the input space. Okay, not the output space, but the input space. The output space, the -1 or +1, is kind of shown by the color here, which you can kind of think of like a third axis, right? So imagine the x is the blue points here being kind of in line with the board, and the red ones being a little bit further above or something like that, right? So these are at -1, this is at +1 in the imaginary z direction. What this separating boundary shows is basically that every point in this region, in the red region, this hypothesis function is positive. That means we're predicting positive there. That means this region is positive, so the sign is 1. In the blue region, the sign is negative. So the sign is -1, so the hypothesis function is negative. And the separating boundary exactly is actually just exactly where the hypothesis function is equal to 0. All right, so that's the mapping of this picture to that formalism I just defined. So it's really important to understand that, right? Because it's not like regression where it's just sort of a visual line. Here, really, what's happening is the hypothesis function, in some sense, is also a function in the third dimension, right? It maps from these 2 inputs and a constant term to some real valued number, which is kind of like the third dimension here. It's actually like a hyperplane that kind of comes out of the board like this. The slide's like this. But this line here is where it crosses 0. And everywhere that function is positive, we say that it's going to classify that point as being positive. And everywhere it's negative, we classify that point as being negative. Again, with the interpretation here that if it's more positive, we are more confident that is really the case. And that kind of corresponds to our intuition here, because if we have a point all the way up there, we're very confident that it's going to be positive. Whereas if we're way down here, we're probably very confident it's actually not a malignant cell. So before I go on, are there any questions with this? Because this is a very important. It's very important to understand how that math translates to that figure. Because oftentimes people sort of get immediately the linear regression setting, and oftentimes they get immediately kind of confused here, and that kind of stops you for a long time in understanding classification. So if there are any questions, please do ask them now. Okay. All right, fingers crossed here. So I think the natural question is, or a natural question that I always have when I think about classification is, okay, this all sounds good. Why don't we just use exactly what we did for regression, right? Because after all, I mean, yes, there are, these are numbers here, or these are discrete choices here, but they're also numbers, right? -1 and +1 still are numbers. Why don't we just use regression with the targets being -1 and +1 and just solve it as a regression problem? And by the way, that actually is not that bad an idea. There are some problems with it, and it's always I'm going to show you kind of a trivial example that makes that work badly. But actually, in practice, that's not a bad idea at all. And so I would actually recommend, and I typically do too, if I want to learn a quick linear classifier, I will just run least squares on it. It's a very effective way of doing things. So don't think that method is not good. It works perfectly fine in a lot of scenarios. But let's talk about why it might not be the best thing to do. So the question really is, how do we define a loss function between our hypothesis prediction and the true label, -1 and +1, right? And we could just use least squares. So if I use least squares, and here's my points, and so now I'm showing actually just a one-dimensional input, and I'm showing my labels on the other axis there. So this is again, more like the regression setting where I'm showing my labels on one or outputs on one axis and inputs on the other one. But what I'm going to do here is I could just treat this like a least squares problem, treat this like a linear regression problem, even though it's not. And I get a fit that looks something like this. So the least squares fit would look something like this. Now, this is an okay fit. It seems to fit the data well. But there is sort of an obvious problem here in that this data actually can be classified perfectly, but by a linear classifier, namely this one, will classify it perfectly. But we're not doing that here. We're actually, for some reason, least squares fit is not giving us the correct classifier, even on even on 5 simple data points here. And so what's happening here is that if you use a least squares type of penalty, you have some of these points over here, right? You have points like this over here. That point is really positive, right? But the least squares penalty says, we can't predict too positively there. You have to predict, exactly 1. You can't predict more than 1. You get penalized for predicting 5 over there, right? And in some sense, that doesn't seem right because we are actually very confident in that point. We are correctly confident in that point. That point is in fact positive. So we shouldn't pay a penalty if we don't predict exactly 1 on that point, but we instead predict, 5 on that point. So there's some notion in which we want a different loss function to capture the qualities of classification tasks over regression tasks. We don't care about predicting exactly 1 for all the positive points and exactly 0 or exactly -1 for all the negative points. We just want to make sure that our predictions are positive for the positive points and negative for the negative points. And they can be really positive or really negative. That's fine. So that's the intuition about why we might want to think about different loss functions. So let's think about a few loss functions now. And in some sense, I think people get a little bit tripped up here because there's sort of an obvious loss function that we would like to be able to use here, which is just the number of times we're right, or actually, I guess for the loss, since we're minimizing it, the number of mistakes we make on the data set. Right? And this is actually called, it actually has a name, it's called 0-1 loss. Or just error sometimes, or mistakes, right? The error if you average it, mistakes if you just take the sum of them. But we're going to call it 0-1 loss here. And the idea here is that the 0-1 loss is 0 if your hypothesis has the same sign as the output. Okay, so if you predict 5 and the output is 1, you suffer 0 loss, you got it right. If you predict 5 and the output is actually, if you predict 5 and the true label is -2, or sorry, -1, those are always -1 and +1. If it's -1, then you're wrong, right? So you suffer a loss of 1. Okay, and the actual only thing I want to emphasize here is that you sort of think of it naturally written in the first way, right? 0 if the sign is equal to that, it's 1 otherwise. But I'm actually going to write it like this. I'm going to write it as 0, 1 loss. Is the indicator. Indicator is a thing that is 1 if it is the inside thing is true, and 0 otherwise. It's the indicator of whether the label times the hypothesis is less than or equal. I use less than or equal to 0 there. Yeah, less than or equal to 0. Okay, so let's think about why that's an equivalent definition. If these two things have the same sign, so they can be both positive or both negative, their product is going to be positive. Okay? So if they have the same sign, their product will be positive. If they have different signs, their product, of course, is going to be negative. Either way, right? It could have, the output could be, label could be +1, our prediction was -5, or the output could be -1, our prediction was 5. This will both cause this whole quantity to be negative. And so whenever this thing is negative, you suffer a loss of 1. Whenever this quantity here is positive, you suffer a loss of 0. If it's exactly 0, you also suffer a loss of 1. That's to avoid the case where you just predict 0 on everything and magically get 100% accuracy, right? We don't want that. So this is the 0, 1 loss. Now there is a problem with this loss, actually, unfortunately, and I won't get into this. We haven't really talked about things like convexity in this course. I don't want to harp on that point either. But the actual problem here is that this loss ends up being what's called NP-hard to optimize when you can't separate the data perfectly. So unless you can separate the data perfectly, i.e. get 0 loss, actually in which case all the losses that we're going to talk about later will also work fine, you can't actually find the linear classifier even that minimizes the total number of errors you make on a data set. It ends up being an NP-hard problem to do that. So that's not too good. The other bad thing is that there's no gradients of this loss. It's non-differentiable, or rather, I guess it's differentiable, but it's not differentiable here because you do an immediate jump there. But it also, the gradient is the derivative is 0 everywhere, or infinite here, right, or undefined here really. So if you make a mistake, and this is kind of also what I talked about, this is actually kind of the setting where we're kind of throwing away everything in the class or in our hypothesis except the sign. So this is kind of the case where we do just predict, the raw output. There's no way that this suggests where we actually move from here, right? So if I'm here, there's no gradient kind of points me downhill towards a position of better loss. I'm just kind of stuck here. So this is a really hard function. The point of all this is a really hard function to optimize. So remember, our problem, our canonical problem was always, and it still is, going to be minimize over theta, the sum from I equals 1 to m of the loss between this example and the prediction and its output. In this case, this is very hard to solve. This is going to be hard for 0, 1 loss. So what do we do instead? What people have done is that they've come up with a lot of other clever alternative losses that kind of accomplish the same thing. And if you really you can kind of even convince yourself maybe that they're really what you want to optimize. You really wanted to optimize these other things, not this one. I think it's kind of a strange argument to a certain extent because you probably want to optimize that. But these other losses are actually also quite reasonable. So here are a bunch of alternative losses to the 0, 1 loss. So I'm showing the 0, 1 loss. Again, what's important here are my axes. So my axis here is the y times the hypothesis value. This means basically, how confident, right or wrong am I? So over here means right and really confident about it. Over here means wrong and really confident about it. So you don't want to be over here, and you do want to be way over there. And then based upon this, we can define different losses about how much we want to penalize you for being over here versus over there. And these have a lot of different names. So for example, the logistic loss is the log of 1 plus the exponential of negative this quantity. As this thing gets very positive, this is going to become, this whole term will become, very big negative. So this x goes to 0. And so you have the log of 1 plus 0, so it equals 0. So as this thing goes, so was the question there? No. As this thing goes, gets really big, you suffer essentially 0 loss, right? It goes to 0. As this thing goes really small, so if this whole thing gets really small, then you take the exponential of negative of a really, I should say, if it gets really large negative magnitude, you take the negative of something big. So this is, this thing might be negative 10, and so this is the exponential of 10. And the log plus 1 of that will approach just the log of the exponential of something. So you approach kind of a linear line going up this way, right? You approach a linear slope there. The hinge loss is another very, and I should say, we'll talk about it in a second, but using this loss, when you use it for classification, that's called logistic regression with this loss function. This loss, called the hinge loss here, that is the max of 1 minus this thing and 0. So that's a term that is linear with a slope of -1 everywhere. It passes exactly to this point here. So sometimes this is kind of like a good upper bound on the 0, 1 loss by some definition of good. And this is also a very popular loss here. If you minimize this thing, this is called the support vector machine. Again, these names are kind of crazy in retrospect, but we're really good at coming up with names in machine learning. Another less common one, but still useful to know, is the exponential loss. That's just the exponential of the negative thing. So again, this gets really, really positive as you go up on this side, and again goes to 0 as you go as your prediction gets more and more correct and more confidently correct. Now, there's some sort of important differences here. So for example, the hinge loss, unlike the other two, actually reaches 0 at a certain point. So if you're more than 1 confident and you're right, you no longer will try to make it any more confident than that, basically. Whereas with logistic loss and hinge and exponential loss, you can always decrease your loss a little bit by getting more and more positive in this case, right? Because it's never actually 0, even though it goes to 0 pretty quickly. So there's some subtle differences here. And sort of with that as an introduction, I want to have a poll question now. With the following question. So take a little time to think about this before. I'm actually going to not open the polls right now. I want you to think about this first. I'll open it in a second. The question here is about sensitivity to outliers. So if I have some points that are, imagine going back here. If I had one point that was benign and was way up in that top right quadrant. The question is, which loss function would be most affected by that? What the questions are saying here is sort of, it's supposed to be an ordering here. So what this would mean is that 0, 1 loss was the least affected, followed by the exponential loss, followed by the hinge and logistic losses kind of in the same class. This would say the exponential loss is least affected, followed by the hinge loss, followed by the logistic loss, followed by the 0, 1 loss that's most affected by that outlier. And by affected here, I mean, it will change the resulting decision boundary when you minimize that loss. So we have a bunch of these things. And then the last one says that outliers don't exist because the output space is bounded. So outliers we had in regression because, we could have a point that was negative 1,000,000, right? But in classification, you don't have that. So maybe outliers don't even exist in classification. OK, so we're going to open this poll up. OK, so this is a good one. For the most part, people got this right. So this one here was the correct answer, and the one that followed was actually the reverse order of it. So I imagine it's just going to be a matter of clarifying which of these two. The rest were kind of nonsensical. I don't know why you would have like 0, 1 followed by exponential followed by hinge logistic. And a few people actually just thought I was making this all up. It's possible. I've had bad questions before. That one about PageRank or whatever, about what happens. That was a bad question. So that wouldn't be the first time. Okay, so does someone want to think why they think it's this one? Let me go back to the slide, actually, because the figure will help. Someone want to say why they think it is number 3? Sorry, number 4? Yeah.
If you have an outlier, then the loss of that is not really high. You shouldn't get to that. So that's why the one that has the higher loss is most sensitive.
Sorry, maybe say that. So the one that has the higher loss will be more sensitive. I see. So basically, yeah. I mean, I think that's the right intuition. So basically, these things will get higher, and so for exponential, they're the highest on this side in some sense. Then followed by kind of these being kind of the same because they're both linear. This being the lowest. So that's the right intuition. Yeah. So that's absolutely right. So just think about this a little bit here, for example. If I have a single point, a single blue point in the top right corner there, for 0, 1 loss, actually, I don't really suffer any penalty at all for that, right? So 0, 1 loss is actually kind of the most possible insensitive loss to outliers because I suffer the exact same loss whether it's right there as I would if it's over there. So it really shouldn't change my decision boundary at all to have some really bad outliers, right? On the other hand, exponential loss is kind of the opposite. Exponential loss, the underlying function here you're sort of being penalized for increases exponentially in that direction, right? Because this is the separating plane, and so any time you're sort of your distance from that plane is basically how much how confident you are. And so if you're all the way over there, you have a very high distance from this plane, and you're very confident, so that will be penalized very, very heavily. And I guess the other leap of logic here is that to realize that if you're being penalized heavily for a point like that, the classifier will then adjust its boundary to account for that. So it will actually kind of push this thing more in that direction so that it doesn't suffer that really high loss. It won't push it all the way over, of course, because then it would suffer high loss on these points. But it will push it over to the point where the sum of all the more losses you suffer here is kind of counteracted by that one loss you suffer from that point way up there. So it will definitely be heavily affected by that, and that will result in the boundary moving to kind of account for that one point. Now the hinge and the logistic losses are kind of in the middle. They both increase linearly as you go away, so that's much slower than, it's much more than constant, no increase, but it's much slower than exponential increase. So you have somewhere in the middle ground where they're still sensitive to outliers to a certain extent, but not nearly as much as something like the exponential loss would be. Yeah.
Do people ever use sigmoid functions for losses?
That's a good question. So the question was, if people use sigmoid functions for losses, so just to be clear, what a sigmoid function is, it would be a negative sigmoid function, right? Because it would look like this. So it's like this. Pardon my drawing there. Believe it or not, that point is supposed to be 0.5, and this is 0 here. It never crosses the lower boundary here. Great. So this is actually a good question. So the sigmoid function is something that looks like this. And it's kind of a smooth version of the 0, 1 loss, right? It sort of gets to the same kind of thing where, as you move further away, you never suffer more than one loss. So it's sort of super insensitive to outliers, but it's also it's smooth. It doesn't have this sort of steep jump there. Maybe it's nicer to optimize it. So the short answer is yes, people have done that plenty, but it's not very common. The reason is that it is still not, again, I'm throwing out terms here that we haven't really covered, but it's not what's called a convex function, meaning that solving the optimization problem actually is still hard. You're still very subject to local optima and things like this when you try to solve an optimization problem, even though you have gradients. Now, the flip side of that is there's plenty of problems people solve all the time that have local optima. All deep learning, all neural networks have local optima. People just solve them anyway. And you could just plug that right in and solve it in a neural network architecture, for instance. But actually, people don't like doing that for the most part because it's still you have this problem of when you're far over here, you can't move this point. So if you have some points that are classified really far over here, the gradient here, while it's not 0, is still really small, and it takes you a very long time to kind of get out of that position to sort of get in the right spot. And what you end up doing is you end up having to kind of initialize things such that most of your points are kind of in this range anyway, kind of in the good range anyway, and then you don't really gain much benefit over, say, logistic loss. And that one has the added advantage that, at least if you have a linear classifier, it actually can be optimized exactly, and it has other benefits as well. So it's doable, but it's just not very common. Yeah. Sorry, can you ask that again? Yes. And so the question is, if there are a lot of outliers, is 0, 1 loss still the optimal solution? Again, optimal here, the nice thing here is that optimal is really a problem definition term, right? So the goal of machine learning is to minimize some loss function. And that is the goal, right? So whatever loss we pick, we say that the goal of our problem is to minimize that one. So if your goal is to minimize error, your accuracy, right, at maximum accuracy, then of course that is by definition the best thing to do is to minimize 0, 1 loss. And if there are a lot of outliers, that could be very different from the loss you get if you minimize some other loss. But the nice thing about machine learning, or I guess nice or not so nice, is that that's not a question of sort of optimal in a true sense. That's optimal in the sense of we're setting up a problem such that we have a measure by which we estimate how bad a point is, and we minimize that. And for the other losses, sometimes you can really minimize them. The challenge is that for 0, 1 loss, you have to figure out how you go about actually minimizing it, not just stating it. Okay. Let's see. All right. So the nice thing, again, and I sort of wrote this already, so I don't have to write it again, is that with this notation, the machine learning approach to classification is exactly the same as what we had for regression. There's no difference between the two domains here. So again, our problem is just, we have our hypothesis function, we define that. We've mainly considered linear ones this class. We'll talk about nonlinear ones next class. Have our hypothesis, we have our loss function, and we have a way of solving this optimization problem. That's the ingredients of a machine learning algorithm there. Now, unlike least squares, even for linear hypothesis classes and these losses which are easier to optimize, like the hinge loss or the logistic loss, this ends up still not having a closed form solution. So there's nothing like least squares where you can just sort of write out a single matrix form and say this is the optimal solution to my parameters that minimize this loss. Instead, we need to resort to solving these optimization problems with gradient descent. And there are other ways as well, but we'll only cover gradient descent here. And really, though other things may be better for kind of smaller scale problems, even for sort of medium-sized problems for these kind of tasks, gradient descent is kind of hard to beat. Gradient descent or some slight modifications can actually be quite hard to beat. So this is a very respectable algorithm for these kinds of problems. Okay, so let's jump into a few examples now of classification algorithms. The first one I'm going to talk about is this, and I'm going to add one more term here, which I haven't introduced before, which we'll talk about a lot more next time, but it is the full definition, so I didn't want to mention this. A support vector machine, and this in particular is a linear support vector machine. One thing you will deal with in the homework are what are called kernel support vector machines. Those essentially are support vector machines that use a very specific type of nonlinear feature, which I'll mention a little bit next lecture, but for the homework it doesn't really matter because you can just sort of treat it as kind of a black box. But I'm talking here about linear support vector machines. So this would be if you specify kernel equals linear in scikit-learn, for example. A support vector machine is all it is just minimizing a hinge loss term, plus actually also what's called a regularization term, which is a penalty on the weights. So actually what we're solving here is we're solving minimize over theta our sum of losses, which are hinge losses, so that was in the form of the max of 1 minus yi times, in this case we'll use a linear, I wrote a linear function here, so theta transpose xi, and 0, plus the sum, plus a what's called the regularization term here, which is the squared norm of the parameters themselves, which is also, you can also write as lambda over 2 of the sum, actually j equals 1 to n of theta j squared. That's the same as the squared 2 norm. We'll talk about this term more next time. This term encourages kind of low weights to your parameters, which is also a way of controlling the complexity of your class. And despite the fact that it's a little bit odd to put it here without introduction, it is true that support vector machines always include that term. So I did want to give you the full story and tell you that is in fact what a real support vector machine is. Now, even actually a little bit more precisely, the standard SVM doesn't actually regularize the theta I corresponding to the constant feature. So it's like a sum of here. If our nth feature was the constant one, it would be actually a sum from I equals n minus, from j equals 1 to n minus 1 of the theta j squared. But that's really has a very minor impact on the actual solution. That's much more for kind of geometric reasons that people do that by convention sometimes. So really ignore this point here, just in case people have seen it before. Now, if you have seen support vector machines before, there's a good chance they were described to you more by way of geometric intuition. So people talk about them being a maximum margin classifier, that if you have points, they kind of find the biggest separating boundary between them, your hyperplane, and other points. And that's true. You can certainly interpret it that way. But I think this is actually a much cleaner interpretation. I think that it's much nicer to think of it in terms of minimizing some loss function plus some additional regularization term. And you don't need to worry about geometry and these kind of things here. This is just a really sort of simple formalism for what it's doing. Now, the way we actually go about solving it, or solving a support vector machine, and again, this is actually one of the best ways of doing it that people actually really run, is just gradient descent. So we're going to take our parameter here and update it according to the direction of the negative gradient. In this case, the negative gradient is kind of hard to, maybe not totally obvious how to do it here. We can actually look at what so what would the gradient of this term here, or what would the derivative really of that max term there be? I have it written down, but you don't have to refer to it. Just the sort of outer term. Actually, what I'm really asking is if we define like a function, like a scalar function, x, as just the max of 1 minus x and 0, what is f prime? Noting that actually this is not actually differentiable because it has this sort of kink at 0, but it's called a subdifferential. It's fine. We'll write it anyway. What is this term? Negative 1? Just negative 1? Yeah, so actually, let's this is actually a good question. Let's just look at the function. So the function looks like this, right? So the function goes through the point 0, 1. It looks kind of like this. And so let's just sort of say what the derivative is, right? In this region, the derivative is always negative 1. Here, it's always 0, right? So this derivative here is just negative 1 if x is less than or equal to 1. I guess the equal case is the hard one here. We don't really know what it is if it's equal, but it's 0 otherwise. And we won't worry about what happens when it's exactly equal to 1. It's an edge case that won't really occur that much. I take that back a little bit, but we definitely won't worry about it here. All right, and we can also write this just as the indicator of the negative indicator, really, of x being less than or equal to 1. So when we now apply the chain rule to compute our gradient here, we take the single derivative of the outer thing and then multiply by the derivative of the inner thing with respect to theta. And so that, or I guess the gradient with respect to theta. And so you just pull out the terms that multiply theta. In that case, that's just yi and xi. So the gradient here would just be the sum from I equals 1 to m of negative y I xi. And I can cancel those negatives, of course, but I just won't bother here. Times the indicator of yi theta transpose xi less than or equal to 1. And then if you also want this thing here, you get the regularization term ends up being just a negative alpha lambda theta term. That comes from this guy here. Okay, so this whole term here is just the gradient with respect to theta of the objective. And the way we update our gradient descent is we just take small steps in that direction. So if we do that, here is the actual parameters that we get. I should say this is actually in a normalized version of it, not in these units. Just like with linear regression, when we run gradient descent, the relative scales here do matter of the different coordinates. And so this is units of thousands here. This is units of ranging between 0.0 and just 0 and 0.2. This is range between 0 and about 2,500. So we do have to we do have to normalize our data in some way. So after normalization, you just run gradient descent and you get parameters like that. That basically gives you what's the weight on feature 1, what's the weight on feature 2, and what's the weight on the constant bias term, the intercept term. But I think more important than this maybe is to sort of look at what happens to the error and the loss function as you optimize, because it's not at all kind of obvious. So here's what happens. So the loss starts out at like 500 or so, and it quickly kind of goes down. Again, this is the total loss of the whole data set. Goes down to this level here. It doesn't go to 0 because the data is not separable. So the loss never actually goes to 0. You'll always suffer some loss, at least with these two features. You will always suffer some loss. You cannot get a perfect classification. With a linear function, right? And that's actually very important. We don't expect to ever get zero loss here, just like you can't fit a line. We couldn't exactly fit a line to the data before because there's always some data above or below the line. Just like that, you're not going to actually get 0 loss here. But we very nicely sort of decrease it, and then with our additional gradient steps, kind of keep decreasing it. This plot here shows the error per iteration. And this is also interesting because for two reasons. First of all, what this shows, kind of interestingly, is that after a single, and you can't even see it. So normally, right, if there's an equal number, and there's not an equal number, but it's not that off, the number of positive and negative examples here. But normally, after you have something error like 40 or 50%, maybe your first time, maybe you just always predict 0, so you get 100% error. But after a single gradient step, the error actually already goes down to about 9%, 9.8%. So one little step in the direction of the gradient is enough to get most of the examples correct. And actually, after that, it does keep going down, but it's kind of almost playing at the margins after that, right? So it gets, one step gets you down to 9.8% error, and many more get you down to 8.8. That's point one, is that oftentimes very few small little updates can actually get you almost all the way there in terms of a classifier. The other thing to notice is that actually at some point we actually had lower error here. So there was actually a point of time where we had lower error than our final level. This is exactly because we are not minimizing the error, right? We're not minimizing 0, 1 loss. This is 0, 1 loss, really, I'm showing, the number of points we get wrong. And we can't minimize that. We're minimizing the hinge loss, which is an approximation, or a surrogate for that, and its minimization actually does not correspond to the point of fewest errors. So this is a real issue. So kind of what we described before, that when you have one of these other losses, we no longer necessarily going to get improve upon all of them, right? We might have a solution that this point here has better hinge loss than this point we stop with, but it actually has higher error. So just be aware that these things can be in conflict like this, even though for the most part one is a good proxy of the other. Okay, so the next class of algorithm that I want to just mention, again, we're covering these actually very fast, but these are sort of common things.
So would it be a good idea if you, like, when you were doing the iterations, also like plot the error and then stop when you reach what you think should be a global minimum?
So should you keep going and then stop when you reach what you think should be a global minimum? So there are a lot. I think there are a lot of ideas there. Some which certainly are good things to do. But I think the bigger issue is that I'm just showing here the loss on the data, what's called the training data. So we will talk about this actually next time and the following time. That's not really what you care about in some sense. You don't really care about how many mistakes I make on this exact data, because I can just memorize this exact data and do perfectly well on it. What we really care about is when I see some new data points, how's that going to do on those? And in that case, you don't have the labels yet. So you don't know what the error is until you do the analysis and have a doctor tell you what the cell actually is. Is it actually a malicious or benign? So while I think it's a good idea to think about what you can do during the training process, about when you can do things like stop optimization earlier than you might want to, I think it's better to think about machine learning as an attempt to minimize some loss. And if you've decided to minimize hinge loss, you should just go ahead and minimize hinge loss. You shouldn't try to minimize some other loss by minimizing hinge loss as a proxy. At least, that's what you're doing in some sense, of course, but at least from an optimization perspective, you should sort of stick with what you're trying to do, because, there might be a point, there might be a point out here that you don't know about until you get to there, right? A point out here that actually has lower loss than both of them, right? It's hard to know that until you've actually run it. Okay, so the next thing we're going to talk about is logistic regression. That is another very, very common algorithm. And all it is plugging in a logistic loss instead of a hinge loss into the same exact framework for machine learning. And again, if you look at these two things, these really aren't too different here, right? So pretty similar, these two lines. They both go to 0 as you go to infinity. Hinge actually hits 0, but logistic kind of creeps down to 0. They both are linear as you go in this direction. They approach a linear function. Hinge is actually linear. This one is the approaches linear. So they're actually quite similar in a lot of ways. And again, a common thing that I see for people that have sort of for data scientists just getting into the field, that I see when you ask them, what's the difference between logistic regression and a support vector machine, is they'll tell you some very complex story about how logistic regression is this probabilistic method that assigns weights to, or assigns a Bernoulli model to something like that, and then support vector machines are this geometric thing that separates the data with hyperplanes and with a maximum margin. But they're actually almost identical to two algorithms. They're very, very similar. They're both just minimizing a loss function on the data, and you can add regularization to a logistic regression as well, and make them essentially identical. Again, not really, because one's smooth and one's not smooth, but that's the difference in some sense. It's just this slight difference in loss function. So again, logistic regression, we just plug in our logistic loss. I won't write it again, but you can kind of see that is the logistic loss there from the previous slide. And our updates are just the gradient of that term there. And if you are want to check your calculus skill, you can see if you can derive this gradient from that loss function. I'll leave that as an exercise for people to do. It's not very hard. It is just like simple calculus here. Yeah. Yeah, so I haven't talked about stochastic gradient descent at all yet, and I actually won't do that for a few more lectures. So this is just gradient descent. It's just I have a loss function. I'm trying to minimize it. I can compute the gradient, and I take steps in that direction. We'll worry about stochastic gradient descent later.
And when do we say that it is converged when everything is classified perfectly?
Oh, no. So the question is, when you say it's converged. So no, I mean, you will never classify everything perfectly here, no matter how long you run it for. It's converged when it stops moving. So there's two ways you can check for convergence. You can check for convergence if the gradient is 0, but probably even more naturally, you check for convergence if the parameter updates aren't changing anymore. So if you start moving your parameters, I mean, this is sort of, I guess I'm not showing here the actual parameters, though I do have those in the notes, so you can look at the notes. They already just run for a fixed number of iterations, but really all I'm doing is I'm just looking at sort of when how the parameters are changing and stopping after a certain point. If you have a smooth function, you can actually look at the value of the gradient. We said that it's 0 when it's unoptimal, so you actually can look at what the gradient actually is to know when to stop. But for practice, honestly, you can just run until things stop changing. You run until this line stops going down. Is the actual sort of answer. Okay. So here's logistic regression. Run for, again, gradient descent, you just run for some iterations. You still have to pick alpha. You have to normalize your data, but we deal with that when we have to. And then here is the logistic regression supporting boundary. And just to emphasize this again, here's logistic regression, and here is the support vector machine. So there's a difference there. There certainly is a difference. But there's not that. They're very, very similar. Right? They're very similar algorithms. They're both minimized and loss function. One's just a little different from the other in terms of the functional form of it. Now, they do have other interpretations. Like logistic regression can give you some sort of probabilistic estimate of how likely, under a certain model, it thinks a class is going to be positive or negative. We will talk about that later when we talk about probability. But I think it's actually kind of almost besides the point in terms of the actual algorithm from a machine learning standpoint, because oftentimes people just throw that away anyway. They just throw away probability and just use the actual hard classification it makes. And in that regime, these are essentially the algorithms are incredibly similar here. And so don't think about the similarities, not the differences between these two different approaches. And the same goes, by the way, for a huge swath of other algorithms too. They're all just sort of very similar in a lot of ways. One very brief point I want to mention here is multi-class classification. So I actually don't want to spend too much time on this, but I do think it's also worth mentioning that there are easy ways in some sense to handle cases where you have more than two classes. So everything we've done so far applied to binary classification, but it turns out actually things are pretty simple to handle with the multi-class case as well. The simplest way to handle this is to, instead of building one classifier for your different for -1 or +1, if you have k classes, you build k different classifiers, each one saying is it class I or not. Okay, so I set up a new data set. I set up k different data sets. Say I'm going to predict is this a dog, a rabbit, or a cat. This picture. I set up one data set that says, is this a dog or not a dog? Another one says, this is a cat or not a cat. And then finally, is this a rabbit or not a rabbit? Right? So I convert it to k different binary classification tasks. And now because I actually do have real valued outputs for all these hypotheses, I can still look at all the individual binary classes, individual binary classifiers, and predict the class of whichever one is most confident, right? So each one of my classifiers will give me some prediction. They'll say, yes, dog with hypothesis 0.5. One will say rabbit, yes, with 1.2, and one will say cat, no, 0, negative 5.2 or whatever, right? So each one will give you its own binary sort of, or not binary, but it will give you a real valued indication of how likely that class is, and you just pick the one that's most positive, most confident in. So this is another advantage of having real valued outputs, because if you just had discrete ones, you could have two classifiers that both said, I think this is a dog, I think it's a rabbit, and how would you compare? Well, with real valued outputs for your hypotheses, you can actually compare them, on equal footing. Yeah.
It's a higher probability.
Yes. Okay.
Whichever is higher probability, that
Yep.
index will be
Yeah. So the question was, why are we using probabilities? So in a classifier like logistic regression, the magnitude will directly correspond to the probability. It's not monotonic, but it's not direct, but it's monotonic. So higher H means higher probability, period. The advantage here is this can encode other classifiers that have nothing to do with probabilities. Like support vector machines don't encode probabilities at all, but you still want to be able to use them here. So it's much better just to use the hypothesis function, the decision function, that sometimes also called, than it is to use than it is to force yourself to use a probability.
in this, like when you're saying like 1 point something, like here we don't have +1, -1, right?
No, I'm saying no. You still have +1 and -1 here. Each H could be positive or negative. If it's positive, it means it thinks it's that class. If it's negative, it means it thinks it's not that class. But each one is a normal binary classifier where the labels are +1 and -1. Any other questions? Okay. Now that actually works fine, but it's not that common, to be honest. People don't typically do that. What people do instead is they actually use a loss function geared towards multi-class classification. And here I want to be very brief because I'm not going to define this very much. But essentially, whereas before we had the hypothesis be a mapping from Rn to R, now we would actually move from having the hypothesis be a mapping from Rn to Rk, where k is the number of classes. And each of those elements in that vector, that k-dimensional vector, define essentially, again, kind of a confidence level for that class. So you have immediately like kind of a confidence that it's this class, a confidence that it's that class, etc. So you actually build something kind of similar in a lot of ways to this, but it's different in that it's a single hypothesis that kind of outputs all the different k values. And then you need to define a loss function that sort of maps between this set of vectors as their prediction, the actual output, and takes those two and combines them to a real number. And I don't want to sort of belabor the point here because it's a little hard to interpret this the first time you see it. But there's actually a very natural generalization of logistic regression or logistic loss that applies to multi-class loss, which is called softmax loss, or sometimes called cross-entropy loss. The form is just right there if you care about it, but I'm not going to go into that form. That actually does penalize you kind of in the right way. Basically, if you put all your weight on the true label, you'll get 0 loss. If you put kind of equal weight around all of them, you kind of get middle loss. If you put a lot of weight on the wrong one, you get very high loss. So it actually is a generalization of logistic loss to the multi-class case, but we won't worry about that too much. Just know that that's the more common thing, is actually define a loss function that directly corresponds to multi-class classification. Okay, so in the last little bit, I just want to highlight a few, and this slide caught up with the right titles there. I want to highlight a few of the libraries that you'll actually be using on the homework for classification with Python. And again, the main library here is going to be the scikit-learn library. And I believe the one that you're using is the support vector classifier for the homework. And I actually want to highlight 2 of them here. 2 of these here are actually going to be the linear. There's also a special class for a linear support vector classifier and support vector classifier, though they actually use different algorithms internally, so be a little careful about that. So I can create a classifier with initializing it with support vector classifier. Kernel equals linear if I want a linear classifier, or with linear SVC, you don't specify that the kernel is linear. For linear SVC, you can specify different losses. So I actually can specify, I believe, logistic loss within the support vector machine classifier. So all these names get really convoluted because that's not a support vector machine anymore. That's now logistic regression, and so it's all very confusing, but you have to kind of get used to it. What's really happening here is that this class is calling a different library that has support for different loss functions. So it uses a hinge loss or maybe even an exponential loss. It can use different things. Whereas the first one, the SVC, always uses a hinge loss. I believe. Maybe there's some other parameter that sets it, but I think it's typically a hinge loss there. And then finally, you call classifier.fit x and y, just like we did before in our least squares case to actually build our classifier. What I described today is what's always called a linear kernel. So that's the case where you just have a linear function. Your hypothesis, again, is just a linear function in your features. That's called a linear kernel. We'll mention next time some other possibilities of other kernels that are not linear for nonlinear classification, but we'll get to that later. And then finally, if you want to predict, you just call the same sort of classifier.predict x. Here, the predict function actually in scikit-learn actually does predict discrete values. It does not predict decision the continuous ones. I forgot to put it there. Maybe I should just put it right now. I'm going to get it wrong, I'm sure, but I think it's called. Does anyone remember? It's called decision function or something like that. The one to get the actual hypothesis function. I think it's called decision function. So this is live coding in PowerPoint, so it's not the most error-resistant method, but I think this is called decision function. I'll verify that, and I'll put it in the notes. So if you want the discrete sort of maximum most likely prediction, you call predict. If you want the actual numerical values, you call decision function. For classifiers that actually are probabilistic, there's another one called predicts_proba, and that's for the probabilities, but there's enough. You have enough things to worry about so far. The other big thing here to keep in mind is that scikit-learn uses different notation than what we discussed here so far. So when we framed a support vector machine, we did the more common thing for machine learning, which is to put the regularizer, to put the sort of coefficient, which again we'll talk about next time, on the regularization term. Scikit-learn actually puts it on the other way. Instead of lambda, it uses a parameter called c, and it weights the loss by c. And it keeps always a 1/2 term on the lambda. So just be aware of that because it does lead to different solutions. That means that, well, we'll get to that later, but basically it means that, bigger c means smaller lambda. So you have to invert how you do the regularization between those two. But again, we'll talk more about regularization next time. So these are really probably the majority of the functions you need to do to know to do the homework, actually. Yeah? They will not produce the same result for random reasons. So the first one, they use different algorithms internally. So the first one uses, I believe, actually I don't know what the first one uses, to be honest. The second one uses a library called liblinear, which does gradient descent or something like gradient descent, or sometimes actually a dual method like gradient descent to solve it quickly. I think the first one probably uses something called SMO, sequential minimal optimization, which is a very different algorithm. So they actually get different solutions, despite the fact that they are the same kind of formalism, because they actually are different machine learning algorithms, because they have that third element of how you solve the optimization problem is different for both of them. There is one more difference too. I believe this one, the linear SVC, actually puts a penalty on the intercept term when you regularize, and the other one doesn't. It does not regularize the intercept term. Again, completely just sort of arbitrary here, but they are slightly different, and they definitely use different optimization techniques. In particular, the linear support vector classifier, if you just run it, the maximum iterations it runs, which is kind of like gradient descent, is actually really low. So it actually probably will not converge if you just run it with default parameters. So you have to run it with a higher number of iterations for it to converge. So these are all things that sort of emphasize one of the main points I want to maybe finish with, which is that scikit-learn is great, but it's very opaque sometimes. And you need to know how they work. It's not like a library for drawing graphics or something like that. Like, you really have to know how these things work in order to use them effectively. Because if you don't know how they work, you're just going to run with the default parameters, because of course that's what you would do, right? And unlike a lot of other libraries that are out there, that often will just break in really strange and unknown ways. So this is actually why I do go kind of pedantically through a lot of this actual mechanics of machine learning here, is because there are weird things that happen with these classifiers if you just try to use them kind of off the shelf. Now, maybe 10 years from now, that won't be the case. I mean, there really will be kind of automated machine learning systems. Companies are certainly trying to do that already to a large degree, but we're still, I think, a ways away from that. So it is important still to know how these things work. And so with that being said, actually here is an alternative way of running a support vector machine, which is the manual way. So this is actually computing gradient descent on a support vector machine, solving it with some number of iterations here and with some alpha. And I'm actually using the lambda formulation, not the other one. So the point here, though, is that, and this is the other flip side, is that yes, so unlike I don't know what's a good example of a third-party library. I don't know, like a web scraping library, right? You don't really, I guess you've written something like that yourselves already. So now I can tell you, you don't really probably need to write your own web scraping library to really do data science. You can use one out there because it's well-defined what it's supposed to do. The other flip side is that they're really long, like a web scraping library, right? You have to really write a lot of code to handle all the cases. Whereas machine learning algorithms are actually quite simple. So this is a full support vector machine in 6 lines of Python code here. And it's totally reasonable, and it will actually work just as well on small problems as the ones that scikit-learn has in them. So it's worth actually, I mean, don't do this. Certainly, use scikit-learn once you're familiar with this, and it's easy for testing things quickly. It's really nice. But it's not bad to try to write some of your own algorithms quickly, because it can be very beneficial, and you will understand how they work as opposed to sort of trusting the default setting, whatever parameters people picked when they wrote scikit-learn. So I think that there's a huge value to understanding and writing those 6 lines of code to actually run gradient descent. And by the way, what this is doing here is that it forms theta. It forms this product of x and y because we have these products in the term there. And then goes number of max iterations. It subtracts. This term here is the gradient of the function of the support vector objective, the hinge loss with respect to theta. And it subtracts alpha times that, and then it returns theta. So that actually does everything you need for a support vector machine to solve it. And it's kind of, it's nice to have a few lines of code that can do something like this, seemingly quite complicated. So. Okay, I have one more here that you can all just code for logistic regression too. You can use it or not. I believe the homework only uses support vector machines, but essentially they're similar things. As with linear regression, you can also access the internal parameters with coefficients and intercepts, but those are just essentially the theta terms that you would learn anyway if you did it yourself. So, okay.